Hello. Let's learn a little bit about stereoisomers and stereochemistry. In this case, we're going to talk about chiral and achiral carbons. When you talk about chiral carbon, what you're really looking at is a carbon that is attached to 4 different atoms or group of atoms. They are also called stereogenic carbons or asymmetric because they don't have symmetry because they are attached to 4 different things. So I'll give you an example. If you have such a carbon right here and that carbon is attached to an OH, a hydrogen, okay, and maybe a chlorine, maybe a bromine. This carbon right here marked with an asterisk is said to be chiral because there's no way you can carry it into equal half. Simply drawn, one would have drawn this carbon like this, without showing the angles, just like Lewis will draw without showing the dashes and wedges. You'll see there's no way you can carry it into equal half. So we say no internal plane of symmetry. So focusing on that carbon, there's no way you can carry it into equal half. This carbon is said to be chiral. On the other hand, if you're looking at achiral carbon, that one might have an internal plane of symmetry, a way to cut it into 2 equal parts. So I'll show you an example. Now assume that we have a hydrogen, those are already 2 similar things, an OH and a Cl. This can be easily drawn suggestively as like this. Okay, so without showing the dashes and the wedges, can be easily drawn, maybe something like this, just to show you that there could be a way of symmetry. Notice that I can easily cut it vertically like this. The hydrogen is reflected on the left side. So this line I've drawn right here, that is what we call internal plane of symmetry. And that carbon is said to be achiral. I will not mark it with an asterisk because we usually mark with an asterisk to refer to one that is chiral. That is achiral because there's an internal plane of symmetry. Okay, so achiral carbon is a carbon attached to at least 2 similar groups or 2 similar atoms or groups of atoms. Okay, how about defining what a stereocenter is and asymmetric carbon? Stereocenter is an atom about which an exchange of 2 groups orientation produces what we call a stereoisomer relationship. The definition of a stereocenter is broader than that of a symmetric carbon. I'll show you what a stereocenter is. I just showed you, so we're going to parallel 2 molecules here. I just showed you the case of OH, Cl, H, and Br. So I'm going to interchange groups here. I'm going to exchange these 2. If I exchange that, the molecules we generate are said to be stereoisomers because they differ in orientation of groups in space. So if I put bromine here and I put chlorine here, those are stereoisomers. And by the way, when assigning R and S stereoisomerism, we will discover that would assign the elements attached to the chiral carbon priority based on the atomic numbers. Bromine will get 1, chlorine will get 2, oxygen will get 3, and since here we are going counterclockwise, we'll call this S. And then if you do the same thing here after exchanging the positions of Cl and Br based on atomic numbers from the periodic table, this one is going 1, 2, 3, and that would be an R. So you see, those are stereoisomers. This carbon right here then qualifies to be called a stereocenter because exchanging two groups produces stereoisomers, in RS in this case. Now, what if you are given an alkene that looks like this? So this versus this. These are also stereoisomers. Let me modify one side so you can see that I swapped the orientation of these two, the positions of those two. Okay, they're exchanged now. So if I am to assign stereoisomerism in alkenes, we use, for this case, because across the double bond we have two different groups, CH3 and OH, CH3 and OH. We'll use, in this case, we'll use cis-trans isomerism. We'll talk about that later. Assigning priorities across the double bond to get the easiest, to get the cis-trans stereoisomerism, oxygen bonded to this carbon of the double bond gets 1 because it has an atomic number of 6, which is higher than hydrogen, which will get 2. Do the same thing this side. Hydrogen has lower atomic number than carbon. You see that the 1s and the 2s are opposites. The 1s and the 2s are opposite, and when that happens across the double bond, we call these trans, usually written in italics. Again, do the same thing here. Hydrogen lower priority on this side, left side carbon high priority based on atomic number, low priority, high priority. You see that the 2s are on the same side or similar side, so we're going to call these Cs. You see, just changing OH and H on one side has changed the stereoisomerism. We get cis and trans. So this carbon is a stereocenter. That's a stereocenter. This is a stereocenter. This is a stereocenter. So it's these two other carbons. Asymmetric carbons are those that contain 4 different atoms or groups of atoms. And all asymmetric centers are also stereocenters. Asymmetric carbons is defined as a carbon that contains 4 different atoms or groups of atoms. By the way, all asymmetric centers are also stereocenters because what we are really defining here is this molecule right here. You see this carbon right here has 4 different groups, right? The OH is different from the Cl, and the Cl is different from the hydrogen, and the hydrogen is different from the bromine. Okay, so this is a symmetric carbon. Now let us do examples. Identify chiral carbons and achiral carbons, and then use that to identify chiral and achiral compounds. So what we will say about chiral compounds is this: if you have a chiral structure, that structure is going to lack internal planar symmetry. So this one lacks internal planar symmetry and also lacks what we call inversion center, a point where if you rotate, you would get internal planar symmetry. Is called an inversion center. But chiral compounds lack internal planar symmetry. Achiral compounds have internal planar symmetry or inversion centers. Achiral compounds, they have internal planar symmetry. You can cut them into equal halves somewhere. Symmetry. So in that case, let me show you an example. If you have a molecule like this, and it has a double bond, and let's say it has a carbon that has 4 different groups on it. Of course, OH is different from hydrogen. This carbon, we are looking at this. And of course, if you cut the molecule into equal half going this way, it's different from going that way. So you see this chiral compound has at least one asymmetric carbon, one chiral carbon, and there is no internal planar symmetry. This is not an internal planar symmetry, so we'll say this is chiral. However, if you draw the same molecule like this, and you have the same OH, you have the implied hydrogen, remember each carbon has four bonds, you can see that this line right here cuts the ring into equal half. So this one is said to be achiral. Okay, it's an achiral compound. This is a chiral compound. Now, if you have a structure like this, you definitely see that the OH is different from the CH3, which is going to be different from the hydrogen. So those are already 3 different things, which is going to be different from the ethyl group. So we have chiral carbon. There's no way to cut this into equal half. There's no internal planar symmetry. Our judgment for this is that this molecule is indeed chiral. And then I'll give you another example. If you have this molecule right here that has an OH and an OH, you definitely see that we can cut the molecule into equal half. Even though these 2 carbons are chiral, they have 4 different things. If you look at them carefully, they have 4 different things. The hydrogen, the OH, the CH3, and the rest of the structure there are different. So this is chiral carbon. Same applies to this. The CH3, the hydrogen, the OH, and the rest of the structure are 4 different groups. However, we have an internal planar symmetry that makes this molecule what we call meso, because it has at least 2 chiral carbons, 2 asymmetric carbons, but it has an internal planar symmetry. Internal planar symmetry, allow me to call it IPS. So in that case, this one is achiral because there is internal planar symmetry somewhere. Now another representation could be in chair form, chair conformation. So let's say you have a chair and you are given an OH axial lap, okay, axial lap, and you're given an OH here, equatorial lap. Is this compound chiral or achiral? The way I reason about this, I draw the 2D because the chair is a 3D, and since it's up, it's gonna get a wedge, and then I see that I skip 2 carbons, maybe 1, 2 I'm skipping. This one is also up, so it's gonna have an OH. You already see that we have multiple internal planar symmetries. We can cut the molecule into equal half, and that alone makes this molecule to be achiral. It's not meso because I don't have 4 different groups. This way and this way is the same. It's just achiral. That is one internal planar symmetry. There is another internal planar symmetry going this way. So that is achiral. Okay, I see what you're asking in your head. You're saying, now what if one of them was a dash? What if one of them was a dash? Like this. It's the same thing, because if I translate this to just without the wedges, you'll see that there is a problem, because the OH and the OH, they all lie on the same plane, cutting plane, like they're on the same plane of cutting. So still this one is achiral, even though this is down and this is up. In other words, if you are to draw the chair, this is how maybe the chair will look like. the most stable chair, you can see that we can carry it into equal half along this plane, and the back side is reflected on the front side of the chair, so still it is a chiral compound. Okay, that is the how to determine chiral and achiral compounds. And I think there's one more example I can show you. If you are given a molecule like this, let me see, let's say you're given bromine, and bromine, you would think that this is dash, this is wedge, and there's no internal plane symmetry, but there is. If you rotate this, this gives you this shape of a molecule. The bromine is gonna go up and away. I'm rotating only the right side. You can rotate whichever side. I'm keeping the left side. This stays. And because rotation of a point along the bond gives you an internal plane of symmetry, this molecule is also a chiral. So watch out for what we call center of inversion. Center of inversion, center of rotation can create internal plane of symmetry, judging the molecule to be a chiral. Okay,